talk about electric fields. From continuous charge distributions. Okay, and so if you go in and we recall, then what we had was that Coulomb's law. From Coulomb's law, we had that, you know, for a point charge, then we could calculate the magnitude of the electric field was given as K times absolute value Q over R squared, where what we looked at was we would have some sort of field charge, Q. I'm going to go ahead and assume my field charge is positive, just for the sake of the diagram. And then what we did was we, looked at some point that I usually label as P. And then what we have is that the distance from the field charge to the point is our value for R. And then we'd evaluate the field at this point. It'd be this magnitude, and since my field charge is positive, they go out away. And so then we would have an electric field that would point like so. Okay? And so what you get is that, in like algebra-based physics, this seems like it is horribly, limiting that really the only formula we have are for point charges. But as you probably realize once you've taken calculus, that gives you everything. Because then that's the whole idea, is that if we have some amount of charge, then what we're going to do is we're going to go in and look at some incremental amount of charge that we'll label in as some sort of dq. So we got some sort of dq in this chunk of charge, and then we're going to find that we want to evaluate the electric field at this particular point. And what you get is you look at the distance from the little incremental amount of charge out to the point, and then with that what we can do is we can calculate the electric field from that little differential element of charge. Now the way I drew the picture, I drew it as if it's a differential volume, but it could be a differential length element or a differential surface element. It can be all sorts of things. And then I'll label this as my dE, so some differential amount of the electric field due to this little dq. And what you have is that our dE magnitude will be K times this dq over R squared. And so the thing is that as you sum over all the little dq's that make up the charge distribution, then the value for R is going to change. The other thing that'll change is the direction on the dE. And so then to add them, since they're all vectors, you're going to need to do components. So we'll need to do some sort of component work. And what we'll get is that the electric field at our point will just be integrating all of these differential electric fields from the little bit of charge. And since they're all vectors, then we're going to need to add, or really what we're doing is integrate by components. Okay, so that's going to be the basic concept there. And so what we can do is we can start by going in and we can take a look at our different types of charge distributions. What we'll have is that for a volume charge distribution, then what we get is that our volume charge density is going to be given as rho. Okay. So this is a lowercase Greek letter called rho. Looks kind of like a curvy P. And you just go around to make the rho. So, and then what you're going to get is that rho will be our dq d volume. And then what we have is that if it is constant, then what we can get is that then rho will be the total charge over the total volume. Okay. All right, so this is the volume case. And then for a surface of charge, so for a surface charge distribution, then the symbol they use is sigma, the lowercase sigma. And this will be our dq dA. Okay, and so this one's sigma, and this is our surface charge density. And then we can talk about that if it is constant, and sigma will be the total charge over the area. Okay. And last but not least, talk about a linear charge distribution. The symbol that they generally use is a lambda. We have some sort of linear charge density. And once again, if it's constant, then we get that it's the charge over the length. Okay. And so these are the general concepts here. Okay. And then what we can very often do is we can use these expressions to solve for our little differential amount of charge, the little, dq type of charge. Okay. And so thus, dq can be given as, rho dv, or it can be given as sigma dA, or it can be given as, lambda dL. And then what we can get is we can take these little differential amounts of charge and we calculate the total charge by integrating them. And so what we would get is we'd integrate rho d volume, or we'd integrate sigma dA, and so on and so forth. So I think you get the idea. Okay.